Warning: hydrochloric acid and sulfuric acid are corrosive. This experiment involves high temperatures and generates large amounts of wastewater, which need to be properly handled.
Hi guys, here is MIH. I posted a video about separating the lanthanide elements from a lighter flint rod quite a long time ago, and I decided to do it again, but in a much more professional standard. I'll be taking the standard industrial approach of oxalate precipitation and ion exchange chromatography used in the 60s to separate individual lanthanide elements in very high purity, usually at 99.99%. Although I'll tell you up front that I failed and didn't manage to separate anything. But anyways, let's go to the actual experiment. My starting material is this mixed oxalate powder containing mostly lanthanum and cerium oxalates, as well as traces of praseodymium and neodymium. This was made by simply dissolving an 100-gram lighter flint in hydrochloric acid and precipitating the rare earths by adding oxalic acid. As you can see, it has a slight yellow to grayish color and it weighs 95 grams. I set up an iron pan on my furnace and heat it to red hot, and add a few spatulas of the oxalate powder. Slowly, the powder touching the bottom of the pan turned yellow. The powder was cooked until it turned to a uniform yellow color. The lanthanide oxalates were decomposing under the heat to various types of products, such as lanthanide oxide and carbonate, as well as carbon monoxide, carbon dioxide, and water. In more detail, the octahydrate or decahydrate of a trivalent lanthanide oxalate first dehydrates to the anhydrous form between 90 and 325 degrees Celsius. Then, the oxalate ion decomposes to carbonate between 350 and 425 degrees Celsius while releasing carbon monoxide gas. Finally, the carbonate is kicked off as carbon dioxide as the temperature increases further to 800 degrees Celsius, and only lanthanide oxide remains. Cerium oxide, on the other hand, decomposes in a different way, first dehydrating and then directly decomposing to cerium-4 oxide while releasing carbon dioxide and carbon monoxide. The cerium was oxidized from +3 to +4, and correspondingly, twice as much carbon monoxide was released compared to before. Praseodymium oxalate decomposes in yet another way, eventually forming praseodymium 3,4 oxide, or PR6O11, containing 4 praseodymium atoms in +4 oxidation state and 2 in +3. Our furnace can only reach about 500 degrees Celsius, so I expect a lot of lanthanide carbonate as well as lanthanide oxide to be produced. Just as a side note, the decomposition proceeds differently when the oxalates are heated in the absence of air, as part of the carbon monoxide disproportionate into carbon, which could contaminate the resulting oxide. Therefore, the mixture needs to be in sufficient contact with the air, which is why I'm stirring it frequently with the spatula. But anyways, bottom line, this decomposition reaction is very complex and occurs in many steps, ultimately producing lanthanide oxides. After I've processed all of the oxalate powder in several batches, I'm left with around 76 grams of lanthanide oxide and carbonate. The next step is to bring it into solution by dissolving it in acid. I wetted the powder with around 50 ml of water to tame the reaction and added a few drops of 20% hydrochloric acid. Contrary of what I thought, nearly no reaction occurred. I then dumped around 30 grams of hydrochloric acid and gases began to release from the mixture. In this reaction, hydrochloric acid reacts with lanthanum, praseodymium, and neodymium oxide or carbonate to produce the corresponding chlorides, while the cerium-4 oxide doesn't react and can be separated from the other lanthanides. However, hydrochloric acid can also react with cerium oxide at higher temperatures, generating small amounts of chlorine, so try to keep the mixture around room temperature and be careful when handling it. When the reaction seems to stop, I stirred the mixture vigorously to ensure a complete reaction. I probably should have grinded the powder before leaching it with acid, since I saw some large chunks flying around, but oh well. The mixture was then filtered to separate the cerium oxide from the lanthanide chloride solution. The filtrate has a light shade of green to it due to the praseodymium ions present, which I thought was very beautiful. The cerium oxide was then washed and dried in air, and its final mass is 38.5 grams, which is equivalent to 31.3 grams of cerium metal, assuming 100% purity. Thus, the 100-gram flint indeed contained a decent amount of cerium. The filtrate contains the rest of the lanthanides, which are lanthanum, praseodymium, and neodymium, and I'm going to attempt to separate them using ion exchange chromatography. How this whole thing works is quite complex, so I'll explain as I go through the experiment. First, I measure out around 100 grams of 732 cationic ion exchange resin. This resin consists of sodium polystyrene sulfonate wetted with water, and its name comes from its ability to swap its sodium ion for other cations. This will be the critical component of the ion exchange column we're about to make. I then added just enough water to submerge the resin and stirred it around to make a slurry. To this slurry, I then add around 10 grams of 20% hydrochloric acid and stirred everything around. In this acid washing step, we convert the resin from its original sodium form into hydrogen form by immersing it in acid. Around 10 minutes later, I poured the resin slurry into my Buchner funnel to remove the acid. As you can see, the acid gained a yellow color, probably due to iron contamination in the resin, so this acid wash step likely serves to remove residual impurities in the resin, which may interfere with the following steps. I then set up the ion exchange column, which is nothing more than a long 50 ml pipette with a piece of cotton stuck at the bottom. Try to put in more cotton than I did here, as I later found that with this amount of cotton, the resin particles are prone to leaking out. More cotton will also slow down the flow rate, which turned out to be a big problem later. I then divided my acid-washed resin into two approximately equal portions, and added 1/2 into the column through a funnel. The resin behaves like a liquid if enough water is added to thin it, and easily fills the column. Note that the ionized water must be used here, as tap water contains mineral ions that could saturate the ion exchange resin and deplete it. The next step is swapping the hydrogen ions in the resin to ammonium, and I add around 100 ml of 5% aqueous solution of ammonium chloride slowly through the top of the column. It eluted off around 10 ml per minute, which was too fast for our ion exchange step later on, so I adjusted the column to slow down the flow rate to the optimal 2 ml per minute. I do this by maintaining an airtight seal between the top of the column and the funnel, so the imbalance in pressure forces the flow rate to slow down. After all of the ammonium chloride is added, I wash the column with the ionized water until the pH of the eluent is around 6 to 7. There are still residual ammonium chloride and hydrochloric acid generated from the reaction, and they need to be removed. Now we have a column filled with ion exchange resin in the ammonium form, and this will be our adsorption column. However, for the separation of the lanthanides to be complete, we need to prepare another separation column. So I filled another pipette with the other half of the acid-washed resin and converted it to the ammonium form as well. I then prepared around 200 ml of 0.3 molar copper sulfate solution in 0.6 molar sulfuric acid. The correct proportion is actually 0.6 molar copper sulfate to 0.3 molar acid, so this may be one of the reasons why I messed the whole thing up later. But anyways, this solution is added to the top of the separation column. As the copper solution runs through the column, a visible color change occurs as the ammonium ions in the resin are swapped by the copper and hydrogen ions. So why are we even doing this? Why do we need to make two columns, and why do we need to add copper to one but not to the other? There are two steps in this entire ion exchange process that takes advantage of the slight difference in the properties of lanthanides, namely adsorption and desorption. If we feed a lanthanide stock solution on top of the adsorption column, the lanthanide ions can swap out the ammonium ions and adsorb on the column. Lanthanum swaps out ammonium ions slightly more readily, so it is concentrated at the top of the column, while neodymium swaps out ammonium slightly poorly, so it is found in the lower part of the column. However, we cannot rely solely on this tiny difference in absorption, as a lot of overlap occurs. Therefore, we add a complexing agent such as EDTA to the column to remove the lanthanides from the resin, a process known as desorption. Different lanthanides also behave differently in this desorption process, with neodymium forming more stable chelates while lanthanum forming less stable ones. Therefore, neodymium, being already at a lower position in the column, gets removed easier, while lanthanum at the top of the column is removed less readily. The net result is that we can widen the gap between the lanthanides by combining the absorption and desorption processes. We can further increase this gap by connecting another separation column, which is what we're making right now. The column is filled with copper ions, which binds more strongly to EDTA. Therefore, when the lanthanide EDTA chelates reach the separation column, the copper replaces the lanthanides to be chelated by EDTA, releasing the lanthanides on the column in the order we said, lanthanum first and neodymium last. After all of the copper is gone with the EDTA, the remaining EDTA again picks up the lanthanides in the order, neodymium first and lanthanum last. The adsorption-desorption process is repeated again on the separation column, which further increases the gap between the lanthanides, resulting in separate bands of elements eluting off the column that we can collect and purify. Now we know why we need to go through this hassle of converting the resin from sodium form to hydrogen, then to ammonium, and finally to copper. Coming back to our column, it has turned to a nearly uniform green color, and its eluent has nearly the same blue color as our original copper solution, so the copper ions are fully loaded onto the resin now. The column was then washed with deionized water until the eluent pH is 6 and no copper ions can be detected. I washed both columns again with deionized water until the eluents are neutral. The two columns with vivid and striking colors are really gorgeous in my opinion, and watching the water flow through the column is really fascinating. Anyways, with our two columns ready, we can now start the actual ion exchange chromatography step. Here is our filtrate from last time, containing around 10 to 20 grams of lanthanide. The ideal concentration is around 40 to 50 grams of lanthanide per liter, so we're about there. Using a pipette, I gradually added the lanthanide chloride solution to the top of the absorption column. The flow rate was a bit too fast, and the solution quickly raced through the column and started coming out. The beaker contained a concentrated solution of oxalic acid. If the resin becomes saturated with lanthanide ions, there will be lanthanide ions left over in the eluent, which will immediately react with the oxalic acid to form a precipitate. Thus, by closely watching the beaker, I can tell when the resin is saturated and the lanthanide ions has penetrated the column. And it looks the penetration is happening right about now. There we go. The dense white precipitate of lanthanide oxalates appear in the beaker. Now I stop adding the lanthanide solution and add deionized water instead to wash out all of the free lanthanide ions in the column. I've added only around 50 ml of my lanthanide solution, so the column could only process a few grams of lanthanides at a time. This is actually a big disadvantage of the ion exchange chromatography process, as it needs large amounts of ion exchange resin to produce a comparatively smaller amount of lanthanides. The eluent also contains a lot of residual lanthanide ions, so by reacting them with oxalic acid, the lanthanides can be recycled and fed back to the process, although I found that the amount was quite small, so I don't bother. When I felt I added enough water, I swapped the large beaker for a smaller beaker containing oxalic acid solution, and apparently no precipitates can be seen, indicating that all of the lanthanides have been washed out. Now it is time to elute the lanthanides out. I stacked the adsorption column on top of the separation column with a little difficulty. This setup is quite dangerous as it is too high and may accidentally be knocked over, so a balancing weight like the bottle of barium carbonate must be included on the iron stand. I then prepared a 0.02 molar disodium EDTA solution by dissolving some disodium EDTA dihydrate in deionized water. This was the second place that I stumbled upon, as the paper called for EDTA-free acid instead of its disodium salt, so I later switched back to true EDTA. The disodium EDTA solution was then added to the top of the columns. As we've said before, it is supposed to elute the lanthanides out of the columns after all of the copper is eluted, so we have to wait until all of the copper is gone. At this point, a lot of problems appeared and things started to lose control. For example, I simply cannot control the flow rate of the EDTA properly, as it is always too fast or too slow, and I can never reach the moderate flow rate like before. Another problem was that the cotton plugs at the bottom of the columns are being squished out by the overwhelming pressure of the resin and the solution, and the column started leaking out spheres of resin. Finally, I had absolutely no idea about the color of the EDTA complexes of the elements, so I cannot tell when all of the copper is gone and lanthanide started coming over. I later found out that the EDTA complex of copper is apparently blue as well, so I can use the blue color to track the copper ions. Adding oxalic acid solution doesn't seem to precipitate anything, as both lanthanide and copper complexes are very stable, and they only react with concentrated oxalic acid at boiling temperatures. Another great thing was that the resin changes color as the copper is eluted off, so by tracking the color change of the column, I can tell where the copper is gone and lanthanide started to come over, although I later became skeptical about this, as I poured a few times the theoretical amounts of EDTA into the column, but the majority of the separation column still remained green. I ultimately called it a day and gave the whole thing up, mainly because of this, as well as 2 successive blunders during my addition of the EDTA solution, which splattered EDTA all over my lab table. Honestly, the main reason why the copper didn't seem to elute is probably the way too fast flow rate, as the literature called for a few hours of separation time, but it is impossible to properly control the flow rate with the pipette. A much better option would be a burette or even an addition funnel, as the stopper could rather accurately control the flow rate of the column. Again, anything I said before were just guesses about how everything works, since I just couldn't find a lot of detailed literature about the process, so I won't challenge anyone if they found out that my deductions are just blatantly wrong. Still, I would say that this project is a much better extension to our previous attempt, and I still observe fascinating phenomena and learn a ton from doing it. So overall, I think this big hassle is ultimately worth it. The next videos are probably about making sodium and the synthesis of some catalysts such as vanadium pentoxide and palladium carbon for some upcoming mega projects, so stay tuned for them. See you soon!